All right, so let's get started with the homework from last week with simple harmonic motion. Now I remember. Friday, we went over the bearings, but I didn't give you homework on that. This was from last Thursday. Okay, so you had some time to do this. So let's take a look. So the first thing we had is write an equation for the simple harmonic motion, that's supposed to be, of a weight at the end of a spring if the weight starts in the neutral position, then falls and recoils. Okay, so you didn't have to draw it out, but it starts here, right? This would be at time equals 0. And then I guess you let it go and it falls, and then it comes back up. Right, so it starts at the center, it dips, it comes up, and it goes like that. All right, so the reason I told you this was because this tells us which function we're using. All right, since we start in the neutral position, that means I'm dealing with the sine function. Because I don't start going up and I start going down, whatever I have, it's going to be negative. All right, so that I'm not sure if we talked about the negative part. So if you didn't have the negative, it won't be completely wrong, right? I'll just take off maybe a point or two for that. All right, so usually they tell you some information to get you started with what am I using, sine or cosine. All right, remember, if I started at the top or at the bottom and then I let go and it did its thing, then that would be cosine. But because I'm starting at the origin or the neutral position, we're going to be using sine. The maximum displacement of the spring is 4. Well, that's pretty easy. That's what goes out in front. That's our amplitude, right? That's how high or low we go, 4 centimeters. And it has a period of 6 seconds. Okay, so this is where, actually, we're going to not use theta. We're going to use time because that's what we've been doing. So for the period, remember, we need our omega here. Now, we don't have an equation for omega straightforward, but we know that the period is equal to 2 pi over omega. So they tell us that the period is 6 seconds. So I have 6 equals 2 pi over omega, and now we're just going to solve. Right? So I have 6 omega equals 2 pi, dividing by 6. Okay, we get 2 pi over 6. We reduce that to pi over 3. So the equation I was looking for number 1 is -4 sine times pi over 3t. Now you can write it a little differently if you'd like. Okay, you can write it as 1 fraction, -4 sine pi t over 3, like that. Either of these are acceptable. All right, that might have been a little hard to type, right? So I gave you the option to upload it as an answer underneath. All right, so if you didn't type it in here, then you could have uploaded the answer here. Any questions about the first one? All right, now the next questions all had to do with the same function here, okay, and that is 5 sine pi over 4t. Okay, so for the first one, or number 2, the first one with this, what is the maximum displacement? Well, that's the number out in front. They don't tell you inches or anything, so the answer there you could just say 5. Right? So the maximum displacement is 5. Right, max displacement equals 5. Let me move this over a little bit so we have some more room. Then they ask us, what is the period? So here we know our omega is pi over 4. So our period is 2 pi over 4. The pi's cancel out. I'm doing 2 divided by 1/4 or 2 times 4. So our period would be 8 seconds. All right, so just be careful when you're simplifying that. All right, so 2 pi divided by pi over 4, keep change flip, and we reduce that to 8 seconds. After the period, I asked you to find the frequency. Well, now that we have the period, frequency is simple. You just flip this. So it would be 1 over 8. Now, depending on how you call it, you could say cycles per second, cycles per s, or however you want to say it. Okay, so that's one thing I didn't mention last week either. Frequency, the units of frequency is always either going to be rotations per second or cycles per second. When we're talking about actual waves, okay, it would be how frequently things happen in 1 second, right? So it's always going to be per unit of time. All right. If you didn't give me units of time, that's fine. But the period is 8, and the frequency is always the reciprocal, so it's going to be 1 over 8. So every second it goes through 1/8 of the cycle. And then for the last one, find the displacement when t equals 6. Now all you had to do here was plug in 6. So you could have done that straightforward. Okay, we are dealing with pi, which means that we have to make sure we are in radian mode. So let me switch over to radian mode. And you can just type it in. 5 sine of pi divided by 4 times 6. All right, now I added an extra set of parentheses for the pi over 4, just to make sure I don't multiply anything. You got to be careful when you're typing in fractions and multiplications in calculators. You can never have too many parentheses, right? So 5 times the sine of pi over 4 times 6 gets us -5. So that means we are at the lowest point in if we're talking about a spring, we're at the lowest point of this spring. All right, so for the last answer, you have D equals -5. Okay, any questions about our simple harmonic motion? Okay. All right, so now going back to what we were talking about. Today, tomorrow, probably Friday, we are going to revisit some of our trig identities. Okay, so here we have the fundamental trig identities. And as I was saying before, you have seen these. These 3 groups are our most common trig identities. The first we have are the reciprocal identities, which just show us the relationship as reciprocals, right? So sine and cosecant are directly related. They are reciprocals of each other. Sine and cosecant, yeah. Cosine and secant are reciprocals of each other. And then the more straightforward one, tangent and cotangent. Okay, don't get confused with these two. I see a lot of confusion there because this is cosine and this is cosecant. This is sine and this is secant, right? So that doesn't go by their names. So sine and cosecant, cosine and secant. The tangent cotangent is pretty straightforward. Then we had the quotient identities, which gave us the tangent and cotangent as a quotient of sine and cosine, or cosine or sine. And then the more difficult ones that we ended up with last time we talked about, these were our Pythagorean identities, which we all get from the unit circle. So the most common we have is sine squared plus cosine squared equals 1. Oh, excuse me. But from that, we can also say that 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. Now, with these, you may see them in radical form. Or it may be beneficial for you to use them in radical form, which just means that we solve for either the sine or the cosine, right? So with this, I could say that sine is equal to the square root of 1 minus cosine squared, right? And we have to add this plus or minus here for 2 reasons. Well, 1, because we're taking the square root, right? And anytime we do that, we have to add the plus or minus. And the second is because our functions, our trig functions, depend on, or I should say the sign of our trig functions depends on what quadrant we're in, right? So remember way back, we have our 4 quadrants, 1, 2, 3, 4, right? And depending on what angle, where our angle is, that tells us, is my sine going to be positive? Is my cosine going to be positive? Are all of them going to be positive? All right, so we're going to have to start to take that into consideration. Before we do that, though, we have some new identities. So if you have room in your old notes, I'd just tag these along. If not, I'd just, maybe put them close to it. This next group are called cofunction identities, and it is a way to relate normal trig functions that don't have a relation. Now, all of these look similar. Make sure I wrote them right. Yep, all of these look similar. And that is because these share a relationship with their periods. So remember, I might have said this before. If I'm adding or subtracting from my angle or from my t or whatever my variable is, that's called the phase shift, right? So that moves us left or right. So actually, let's take a look. So the sine of pi over 2 minus theta is cosine over theta. So if I graph both of those, so if I graph cosine of x, and if I graph sine of pi over 2 minus x, they are the same function, right? Because the period and the phase shift give us the same function there when we do the pi minus 2, pi over 2. Right, we can see that they are the same line, right? As I click on one, it just overlaps the other. Right, so if I shift sine over pi over 2, that gives me my cosine function. Okay, and if I do the same, if I shift the cosine over pi over 2, that gives me the sine function. And I talked about this briefly. I didn't, I might have showed you on the graph. I don't know if I gave you an exact equation like we have here, but I have referenced it. But now we also have a relationship between the others. Oops, no, stop. I don't want that. Nope. Oh no. Oops, I got rid of the objective. And I'm still writing. Okay. So now we also have that the tangent and cotangent have the same relationship, and secant and cosecant have the same relationship. All right, so we have 6 different individual parts here, but we have pairs that go with each other. All right, so the sine and cosine, tan and cotan, secant and cosecant. Oh, full of yawns today. Tired. And we have one more, which involves a little bit of algebra. And these are even and odd identities. Now, what's nice about our trig functions is they are all either even or odd. Going back to algebra, an even function would be like x squared. So an even function, if I change the sign of what I plug in, I get the same answer. So 2 squared gets me 4, positive 4. Negative 2 squared also gets me positive 4. So I change the sign of the input, but I still get the same output. Cosine and secant are both even functions. Okay, the cosine of negative 90 degrees is the same as the cosine of 90 degrees. The cosine of 10 pi over 11 is the same as the cosine as negative 10 pi over 11. Right? So that's a neat trick that you can use, or a quick tool. So you don't really have to worry about the sign if you're doing cosine or secant. It's the same as if you plugged in something positive. So again, if you have the cosine of negative 320 degrees, well, you can find the cosine of positive 320 degrees, and they would be the same. The other 4 are all odd functions, which means that if you make the input negative, that's going to make your answer negative. So the sine of 45 gets us root 2 over 2. The sine of negative 45, so I made the input negative, would get me negative root 2 over 2. It would make the answer negative. Okay, so that's true for sine, cosecant, tangent, and cotangent. All right, so I'll give you a few minutes to finish copying down this. But I think that's, since I forgot about the homework, I don't want to jump into an example right now and get caught up with the time. So I will leave you with these new identities, the cofunction and even and odd identities. And that's going to be it for us today.